This is my video solution for question 3 of a set of 5 questions recently released by BFW. These 5 questions aren't official College Board questions, but they were written to be of a similar style and difficulty, and you can download a PDF of the questions themselves via the link I provided in the description below. And I really encourage you to attempt the questions on your own before watching my solution videos. Now, in one of my previous video solutions, specifically the one for question 2 of this set, I included a number of tips on how to write paragraph-style questions on the AP Physics exams in general. So if you haven't seen that video yet, I'd really encourage you to watch that one before you watch this video, as I'll primarily be focusing on the specific question here in this video and less so on general tips. So with that said, I'm going to get right into this question. So we're told that this is a question that should take us about 15 minutes, and as you can see, it is the second paragraph example from this set of 5 questions. It's actually question number 3 of the whole set, though. So we are given a scenario that includes 2 identical carts, and as soon as I see that, I'm thinking that they have the same mass, among other things. They're set to collide on a track in a physics classroom. We're told to assume that we may neglect friction, which makes things a lot nicer than if there had been friction. So there's no friction between the carts and the track. And there are motion detectors set up to measure the velocity of each cart, both before and after the collision, which grants us access to a lot of information. The bumpers on the carts can be adjusted to change the elasticity of the collision. If you've worked with actual carts in a physics lab, you may have seen carts that are capable of doing that. Depending on how you set them up, they could be very bouncy, often with a little spring-loaded mechanism. They might stick together with often Velcro or magnets. You get the idea. We can adjust that and have different collisions even using the same carts. So there are 3 trials run with different elasticity settings for the same initial velocities, and they result in 3 different final conditions. They are referred to as trials A, B, and C, and here's what happens in each of them. In trial A, the 2 carts come to rest as a result of the collision. So visualize 2 carts approaching one another, they hit, they stick together, they remain stationary from that point on. In trial B, the 2 carts bounce off of each other and exchange velocities. So exchanging velocities, basically try to imagine that whatever they came in at, the 2 carts are approaching each other, they bounce off of each other, and basically retain the same speeds that they had before, but of course are in opposite directions. So that's what is kind of meant by the exchange velocities, especially since they must have had the same speeds as each other, as we'll discuss shortly. In trial C, the 2 carts again bounce off of each other, but this time they move off with lower speeds than they had before the collision. So that's going to have important implications for energy right away. Our job is to write again a clear, coherent, paragraph-length response to identify the types of collisions in each of the 3 trials, and also for each trial we're to describe the center of mass velocity before, during, and after the collisions. And by the way, this callout for during the collision is kind of similar to one of the earlier solutions that I made for a different question, in which we're really not able to simplify the collision to assuming that it took 0 time, which we sometimes like to do for simplicity, but I don't think we're going to be able to get away with that here. We're going to have to consider the collision itself as having a small but non-ignorable amount of time to occur. So we are also asked to describe any energy changes during the interaction. So again, during the interaction, that's what I was just talking about, that it's not able to be simplified as having been 0 interval of time, and clearly listing the objects in our system. I've already written up my solution. I'm just going to present it to you, go through it quickly, and then I'll go through the points to show you where I would have earned each one of those points. So here is what I would consider to be an example of a good response. And as you can see, it's a bit lengthy, but that's largely me trying to be extra clear for the sake of you, students, hopefully, watching this video. It certainly could have been given in a more briefer form and still conveyed the same information. So here it is. In this answer, I say, I'll be considering the system composed of the 2 carts only, so I'm not including the track, I'm not including Earth, etc., just the 2 carts, which I think is the simplest but still meaningful thing I could have done, and I think certainly the intent of the question. By the law of conservation of momentum, in each trial, both the momentum of the system and the velocity of its center of mass must have been constant before, during, and after the collision, as there was no external force exerted onto the system. So this is me calling out a very, very specific idea in physics, the law of conservation of momentum, and specifically explaining how it pertains to this particular situation. There's no external force provided to the system. I then go on to elaborate to explain how I've come to that conclusion, specifically saying that there were no external horizontal forces, as the carts move with negligible friction, and there's really no other contender here for an external force. If you're thinking of the collision itself, I'll remind you that yes, it would be true that each cart would exert force on the other cart, but both carts are in my system, so those would be internal forces. And I'm only considering external forces, as only external forces can change the momentum of my system. I also elaborate that the vertical forces would be, in effect, balanced with the force of gravity down and a normal force upwards. So definitely no net force in either horizontal or vertical. I then go on to specifically talk about each trial. And as you can see, I kind of broke this up a little bit. So yeah, it's not exactly a quote paragraph, but I've discussed that in an earlier video. The collision in trial A is perfectly elastic. So that's one of the things I was asked to do, identifying the collision types. I explain how I've come to that conclusion, as the collision in this trial resulted in the carts sticking together, and so the collision dissipated the maximum amount of kinetic energy possible, and in this case, since they came to be stationary, all of it in this case. So just for the record, having the objects collide and stick is really the distinguishing feature of an inelastic collision. It's not actually necessary that they come to rest. Although if they come to rest, they're necessarily together at the same velocity, which is to say that they've effectively stuck together. The kinetic energy that was present before the collision was transformed into other forms of energy, some of which would be expected to remain in the system as internal energy, in other words, warmth, kind of a thermal energy, and some of which would be lost to the system, to the environment. I don't know, maybe some energy was transferred to the track, and or the air, sound, etc. So just being a little bit vague here, but just mentioning that it's possible we lost some energy from our system. This also tells us that the two carts must have started, and this is something I kind of hinted at a little while ago, they must have started with zero net momentum, since it ends up with zero net momentum, which means that the velocity of the center of mass in all three trials, not just the one we're talking about right now, but all three trials was zero, since they started with the same initial velocities in all three cases. That's really important. All three trials have basically a symmetry of sorts. The carts must have been coming at each other with identical speeds, since they have identical masses, and we know that the system has zero net momentum in all three cases. So moving on to trial B, I'll hone in on what is specifically different about it. The collision in trial B is perfectly elastic. During the collision itself, at least some kinetic energy was first transformed into internal energy, which probably would be a form that you might want to call elastic potential energy, especially if you're thinking of something like a spring mechanism in these carts. But all of this internal energy was quickly transformed back into kinetic energy, which is what makes this an elastic collision. So for the record, elastic collisions don't retain a, quote, constant kinetic energy. I've seen that written many times or said many times as not quite correct. That would only be true if we really are justified in pretending that the collision took zero time to occur. But really, those carts would have had to abruptly slow down, stop, basically reverse direction of travel, going faster, faster, faster until they depart from one another. So the kinetic energy is not actually constant. It's actually lost momentarily, but the key feature here is that it's stored in a form that can be actually transformed back into kinetic energy with ease, and in this case, ideally, all of it. I just remind that the velocity of the center mass was zero and constant as described above. So I've already covered that, but I thought just for clarity, I would include that additionally here since I'm talking about collision B specifically here. The collision in trial C is inelastic. Specifically, what I mean by that is the collision transformed at least some of the kinetic energy into internal energy, and some but not all of that energy was transformed back into kinetic energy. The velocity of the center mass was again zero and constant, as I've already discussed. So that should do it. I think that I've done everything that they've asked me to do within the question itself, touching upon the types of collisions, the center mass velocity before, during, and after. Let's go through the points and see exactly where I've earned them. Maybe to do so, I will clear off the highlighting that I just did temporarily there. So clean this up a little bit and then look at the points. Perfect. Okay. So this question was worth a total of 9 points, and we'll look at each one of them in turn here. So the first point, 1 point, is for identifying that the center of mass velocity is constant. Okay, so the center of mass velocity is constant unless an external force is exerted. So did I mention that fact? Yes, I did. I said that pretty early on, in fact. So I said the center of mass velocity must have been constant, and I even elaborate to say that there was no net force, etc. So that first point is well included early on in my answer. Moving on to the second point. Let's see, momentum is always conserved since we can neglect friction. Momentum is constant. So we have constant momentum because, well, I wouldn't specifically say friction alone, but more generally there's no net forces there to change that. So do I call out the law of conservation of momentum and specifically talking about forces? And of course, yes, I did. Since the law of conservation of momentum, I called it out right there. And I have it in my answer kind of tied into that center of mass velocity. But again, I'm referring to there being no net external forces that would otherwise be able to change that momentum. So I think that together, that first sentence or two of my answer really covers both of those points. Next point. Point 3, or the third point, for all 3 cases, the center of mass velocity is the same. So, and of course that can be implied by stating that the momentum is the same in all 3 cases. So the center of mass velocity is the same in all 3 cases. I think I explicitly said that, again, pretty early on, where I said, this also tells us the 2 cars must have, oh yeah, right here. The velocity of the center mass in all 3 trials was, I didn't just say the same, I actually called out that it was specifically 0 in all 3 cases, since they had the same starting conditions. So I've got that point well covered in my solution. Next point. Let's see, point, I'll switch to a kind of a highlighter. 1 point for saying that for using a correct statement that the kinetic energy changes into other types of energy during a collision. So this happens more than once, but I think if it occurred anywhere in our answer, it would qualify for that point. So kinetic energy changing to other types of energy during a collision, and I did that more than once, so let me just identify the first time I happen to have mentioned it, I think was in the first collision. So let's see here, so where did I talk about that specifically? Kinetic energy that was present, right here. The kinetic energy that was present before the collision was transformed into other types of energy, and I go on to elaborate specifically internal energy, etc. But you can see that I have that well covered there. Okay, next point. 1 point for a correct use of the concept that the amount of kinetic energy not restored determines the collision type. So we were asked to classify the 3 collisions. We're going to have to perform that classification based on what happened to the kinetic energy. And of course, I did that in each of the 3 trials, so I'll just call it out in any one of them to illustrate that that point was earned. Let's see here. Some kinetic energy was transformed, which makes this okay, right here. This is a good example. So some kinetic energy was transformed, etc., but then it all quickly transformed back, which is what makes this an elastic collision. So I'm classifying the collision based upon what happened to the kinetic energy. Earns that point. Next point. For a correct statement that in elastic collisions specifically, all kinetic energy is restored. So we have to call out specifically for elastic collisions. And of course, that was collision B, I think, right? So trial B is perfectly elastic. And why have I come to, or how have I come to that conclusion? Because it was all quickly transformed back into kinetic energy. So I've already kind of utilized that sentence, but it's covering more than 1 point. So it's good. Next point. For a statement that during inelastic collisions, some of the internal energy is converted into other types of energy. Or you could say that it was dissipated. So some indication that in elastic collisions, kinetic energy is not restored fully as kinetic energy. And I say that again more than once, I believe. Let's call it out here. So in trial C, it was inelastic. At least some of the energy was transformed into internal energy, but again, not all of it. In fact, probably the better example, I think I called it out specifically in trial A, where I think I said it was specifically dissipated somewhere in there. Yeah, here. So the collision was dissipated, so in either place, I'm pretty well covered for that point. 2 more points, and I'm kind of running out of colors here, so let's quickly switch this one off for something else. Ooh, I don't know, let's use a purple. So 1 point for correctly finding the center of mass velocity. So we were tasked to actually find the center of mass, and I did that. It was the same in all 3 collisions. In fact, I have it right here. It's kind of doubling up on here since I specifically called it out. The velocity of the center of mass in all 3 trials was 0. And I explained why that was true, so that would earn me that point. The last point is more of a generalized point, as we've seen before. Just kind of holistically speaking, is the whole answer logical, relevant, internally consistent, etc.? And I would argue that, yes, it is. It's fairly well laid out. It should flow nicely. I don't have any incorrect statements. I don't really go into anything that is irrelevant to the situation at hand. So that point should easily be earned. So there you have it. This is a full point. And the end of this video. I will be working on more solution videos as soon as I can.